Welcome to the April Tech Talk. I'm Olivia Lynn, and our co-host is Colin Orion Chandler. We're both members of LINCC Frameworks, I as a software developer, and Colin as a project scientist. I'm at Carnegie Mellon University, and Colin is at the Dirac Institute and University of Washington. LINCC Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, here we highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss the efforts of interest in the analyses of LSST data. LINCC Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific or 1 p.m. Eastern. Our speaker today is Mi Dai. Mi is a project scientist at the University of Pittsburgh and here at LINCC Frameworks, and among other work, is a core member of the LightCurveLynx team. For the talk, please ask questions in Zoom or in the LINCC Tech Talks channel of the Discovery Alliance Slack. On Zoom, you can type questions into chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel. With that, Mi, please take it away.
All right, thank you, Olivia. Hi everyone. I am very happy to present you the LightCurveLynx package that we have been developing within the LINCC Frameworks team. So before I get started, um, I will just recognize all the core team member that has been putting effort developing the software, and also our external contributors who have been contributed to the code base in different ways. Um, Okay, so what is LightCurveLynx? LightCurveLynx is a package that provides a flexible, scalable, and user-friendly time domain simulation software with realistic effects and service strategies. So on this right plot, you can see this is an example of a simulated LSST supernova light curves. So the motivation behind developing this software is because this kind of catalog level simulations are very useful for a variety of things, like forecasting the discovery rate of different transients and variables, and optimizing service strategy, characterizing biases, and mitigation of these biases in various depths of analysis. And simulations are very important for training machine learning algorithms, providing like training set and data augmentations. So this is even more important when we have these next generation telescopes such as the Roman Observatory and Roman, because we're having like so much more data and more sophisticated algorithm are being developed using all these kind of simulations. So the goal when we start to develop this software is making it as useful as possible, as flexible as possible, and we use best software practice and including continuous integration unit test and a very extensive list of documentations. As we build this software, we also find that one thing that we extend to this goal is we found we can build directly on many existing simulation packages so that we can not duplicate effort, but like taking advantage of all the things people have been already building in, but using these in a uniform, unified framework. So here I show a first glance of the workflow or pipeline for this software, how a simulation from the end-to-end simulation would work. So there are a bunch of colored important components in this diagram. and I will show all of these in the following slides. But as a summary, we start from a parameter model, which will define all your parameter distributions that describes your actual physical model, which describes your how your transient or variable stars behaves. Um, and then we have this observed table, which takes in the survey data, including cadence, survey conditions, and filter information, all these things, and we use summarize that into a observed table, and we can use them to efficiently match time and filters that can be put in as a parameter to your physical model. And then we apply effects. This includes things like Milky Way extinction or host galaxy extinction, lensing, all these kinds of things. And then if we're doing a extragalactic model, we usually have to uh, redshift it and then integrate it over passband to get the actual perfect fluxes. But we can also support a band pass model, which you do not need to start from the SCD level, but just having the pre-calculated band fluxes and uh, compute the flux from there. So once we have these noise-free band fluxes, we apply some noise model and then obtain the observed band fluxes. That will be our final light curves showing as this. So one of the first thing I would like to highlight is we use efficient spatial matching and observed table filtering so that we don't need to store a oversampled light curve, which improves efficiency. So through the talk, I will show examples, and I will talk a lot about a type 1A supernova SED model. So I just use this slide to summarize it in case you're not familiar with what a type 1A supernova cosmology does. So this is a model called SALT, which is basically a averaged spectral sequence for a typical type 1A supernova plus some variations summarized in these two components, M0 and M1, and also this one component color law that would apply to the SCD and characterize the color variations in a supernova. So now let's go back and talk about every different component of the first thing I wanted to talk is the parameter sampling or the parameter model you see in our pipeline diagram. So let's start with a very simple example. So source fluxes depends on a range of model parameters that can also depend on hyperparameters. And for this very simple example, we want to simulate some supernova using the SALT model I just mentioned with a location draw uniformly from a sphere and a uniform distribution of redshift. And these parameters from the SALT model that can be some uniform distribution or some predefined distribution. This is very simple and not really realistic. And a more realistic case would be we simulate this supernova using the SALT model, and we sample RA and DAC from the host galaxy, and this host galaxy can also have other properties that we can simulate using some flow like PZ flow model, and we can assign the location of the supernova as following some distribution as offset from the host galaxy center. And we can sample these light curve parameters using different realistic distributions. For example, we can sample the X1 distribution related to the host galaxy stellar mass and a Gaussian distribution of the color and the X0 distribution pre-calculated using cosmology that also related to X1 and C as a step of standardization of the supernova. So this would require a combination of sampling and computation. And this diagram summarizes what I have described in words. So basically, we need these complicated network to describe what diagram to describe what we would like to simulate. But we wanted to make the definition, make writing this definition of all these parameters as close as Python programming. So hopefully it can be easily taken when you are just getting started to use it. So this is a way that we define a model and define all the distributions of all the parameters. And I'll describe in a bit more details in the next couple slides. So first of all, the sources are objects whose parameters are set as constructor or arguments. So every parameter here would have would like be described as a line as one of the parameters of this model. And there are different ways that you can define the parameter. For example, it can be just a constant. It can be referenced from some other part of the model as attribute. In this case, we first define a host galaxy, and then we can take the host galaxy redshift as the redshift of the supernova. And then we can set the parameter as a result of sampling a NumPy or SciPy distribution. We can, so the distribution can also depend on other parameters in the model. For example, if we define a host galaxy with their RA and DEC, we can refer to the location of the supernova as a Gaussian distribution from the center of the host galaxy RA and DEC with some scaling factor. We can also define this parameter as a function, with the function also depend on other user-defined functions. So this way, like you basically chain your parameters like the way you would do when drawing this diagram that represents how your relations of parameters related. So it is very important that the values of each parameters are the same at each stage. And this is all handled by LightCurveLynx internally. So the fun part of using LightCurveLynx, we like to think these different parts as Lego blocks. So we can mix and match all these different parts and to generate your favorite simulations. So currently we have a lot of things supported. For example, one of the things I mentioned as the observe table, which defines how the survey behaves and how the cadence and all those survey conditions are. And we have support for these different surveys listed here. And for the source or the physical model, we call it, we already can support a bunch of different things. For example, SN Cosmo is one popular package for simulating supernova, and Redback is a popular package for simulating a lot of high energy events. And there are also all these things that I will not go one by one. Um, and for effects, we currently have dust extinction and microlensing, uh, and we support user-defined effects if something is important that you want to simulate. For parameter model, I mentioned we can sample from any NumPy random distributions or SciPy random distributions. We also have support for things like PZ-flow and BellB and some like a tabular data distributions and functions of other parameters. So I will, in this talk, give an example of simulating a sample of type 1A supernova from the ZTF sample. And I'll hopefully walk you through different components and uh, let you know how these things works so that you will take this, you will be able to take this and make your own simulation after this. So this blue square and dots is highlighting what I will be using. So basically, I'm using a ZTF survey with the salt model I just described, and we will add something like dust extinction effect. Well, mainly Milky Way extinction in this case, and we'll sample from a few different parameter distributions that I will describe in a bit. So, we hope things are all straightforward and easy. So the first thing you would to know for simulating a light curve is this simulate light curve function, which takes these parameters that I will describe one by one. But they basically, these are all you would need when you want to simulate a thing. So we will need a source describes like basically a physical model describes what your source looks like. We can define how many samples you want to simulate, and then we will need to define a observed table object that um, defines like all the observing conditions. And we'll also need a passband which a passband group which tells the software how you would like to integrate your SCDs to the passband. And we have some built-in parallel computing functions. So if you're like me that don't know a lot about parallel computing, you could just use these two lines to add a batch size and number of jobs, and we will take care of all the parallel computing needs. We also support a bunch of different parallel computing softwares. So those are described in our documentations. So I will describe these different components one by one. Let's start from the simplest. So observe table. Uh, okay, so I am showing this example that we start from reading in a observing log, which is a public which is published in the ZTF SN1ADR2 paper. Um, and we also combined it with some other metadata from the public ZTF release. And basically, we just read in this table, and we would want to define some column mapping that will be used internally for when we do observing table matching. And we want to define a detector footprint that represents the ZTF camera footprint. And then we basically just use this predefined ZTF observed table object to input all these informations. So we have pre-written this ZTF observed table so that if you would like to simulate ZTF and you have related information such as a observing log or something equivalent, we can just take in this object and use it directly. And there are a few things we also support. For example, we can use the LSST observed table to simulate currently the DP1 and DP2, where we can take in the what we call it visit table and simulate the data that has already been taken. And we can also simulate the OPSIM table that was like a simulated schedule from the LSST project. We can simulate, we have this Roman observed table to simulate Roman. We also have support for SkyMapper, ZTF, and the August survey data. And the next part would be the passband, which is really just one easy line that's reading from a preset. In our case, it's ZTF. And the list of filters and can also be defined. And we have a few convenient ways to define a passband from a variety of sources. For example, you can use that SVO service that have lots of filter transmission information summarized, and you can directly read from a file, and you can read from IsonCosmo, which also have a bunch of passband defined. Now here comes from the physical model that would define that basically describes how the transient, the supernova behave. And this will be coupled with the parameter model as I have described earlier. For simulating this ZTF sample, we want to use some volumetric rate from the literature, and we can calculate the number of supernova based on this rate and the redshift distribution based on this rate. And then we can simulate, we can generate RA and DAC from some uniform sampling from the actual footprint of the survey. And we can use this PZ flow model and reading some pre-trained PZ flow distributions that we can draw to generate supernova light curve parameters and host galaxy parameters. So we first define a host, which, as I have described before, it's a simple one with RAN DAC, and a host galaxy stellar mass comes from the PZ flow sample. And we can do this self-defined sample PDF and provide a PDF, provide a customized PDF to be sampled for the redshift. And then we define this source or physical model as using this SN-Cosmo wrapper model, which basically wraps the SN-Cosmo, the SOL3 model in SN-Cosmo. Well, okay, so it wraps like all the SN-Cosmo model, and we're using SOL3 here. So these are all the necessary parameters listed. T0 is a reference time that usually we describe the peak of the supernova, and then X0 is a scaling amplitude factor that describes the brightness of the supernova, and then X1 and C are light curve parameters. And RA and DAC would be the location of the supernova, the redshift, and then we can also apply some extrapolation to in the case that the model didn't define the full time range that we want to sample. So as you can see from this definition, we have used a combination of different ways to specify the distributions, like a NumPy random function, like a self user-defined function, and using some pgflow model and coding redshift from the host galaxies. So all these combinations make it very easy to define things all within this one block. And after we define the source, we can apply a Milky Way extinction. We load a dust map, and then using the predefined extinction effect that takes into account that uses the extinction parameter from the dust map. And then we use add effect to add one of these effects to the source so that everything would be combined and simulate together. So here I show this line of code that simulates the light curves again, as we have covered all of these different components. So next, I would like to mention about noise calculation, since that is sort of hidden internally in the code and not really represented in that line of code. So we calculate pulsar noise using sky background, PSF, 0 points, and CCD characterizations. And then we draw a random flux, assuming it's a Gaussian centered at the perfect flux with the calculated flux error. The noise calculation is defined in the observed table. So each of these surveys I have mentioned who has an observed table we already written, there is a noise calculation part. And if you are well, you could take a look and see if that satisfies what you think the noise calculation would be look like, and you could also make changes to satisfy whatever your needs in terms of noise calculation. So we run this code and we can generate some light curves, and as a result, we summarize these light curves. We put these light curves into a nested data frame using the nested pandas package, which is also developed within the LINCC frameworks. So in this format, we will have this single table with each row per source, and we have metadata as these like single row and columns, and this nested column that have all the light curve information in this. I would highly recommend this because this can make things easy when you try to process your light curve. For example, after we simulate the light curve, we would like to apply a selection function as shown in this plot on the right, upper right. This is a selection function based on the bright transient survey from ZTF. And by defining this and draw like a random probability, we would able to assign a selection, pass a selection, pass specific spectroscopic selection tag to all the light curves. And we would just use this one reduce. I think this is actually a little out of date. The newer version would be map rows for this nested column and apply this function to all the light curves in the table. So now I will flash through some results. This is one of the example light curve we simulate and compare with the actual ZTF observations. So the solid dots is the actual observation, and the shaded dots is 100 realizations of this same supernova using the best fit light curve parameters from this supernova. And on the bottom, I'm showing the ratios of the signal to noise ratio between between simulation and data. And well, you see, we are basically recovering most part of this light curve, and we are slightly underestimating the error for this single case, but everything seems to be pretty consistent. And when we simulate a full sample, we can compare the redshift distribution. So I'm showing the simulation in blue and orange as the actual ZTF supernova 180R2 data. And we also fed to a skewed Gaussian model, and we see we get pretty consistent result with the simulation representing the data distribution. And so we try to simulate this salt parameter x1 and host stellar mass as a joint distribution using PZ flow, and we show comparing to the data, we are able to simulate the same distribution as the data is showing. And here I'm showing some of the comparisons of the fluxes and errors. Again, blue is data and orange, blue is simulation and orange is data. And on the left, I'm showing all the fluxes and errors and their contour and 2D contours. And we see we are mostly covering all the recovered all the flux and error spaces as the data is covering. And on the right, I'm showing just the maximum flux and the error at that maximum flux and their 2D contours. And again, we are matching, our simulation is matching the data pretty well. And in terms of computation cost, for this example, we simulate about 84,000 of supernova with 8 jobs and 5,000 in a batch. The CPU time we have is around 25 seconds with the wall time about 4 minutes. So I have some additional highlights that are not shown in the specific example. So we can support, as I have mentioned, existing completed surveys, for example, ZTF or Rubin DP1 and DP2. And we can also simulate using survey forecasts, for example, using the Rubin OpSims, the Argus survey, and the Roman survey. And you can also define your own survey and simulate using it. And we also support joint surveys. So when you simulate, you can define the surveys as a list of surveys so that it will jointly simulate things together. And we support both SED level and photometry or band flex level simulations. In the example, I'm showing the SALT model, which is a SED level model. But for like things like galactic objects, there's no need to do redshifting, so it's likely better to just use a band flex model. And we have documentations here and there for you to look at. We also have limited spectral simulation supported. This is still under development. And I am showing, listing a bunch of examples that have been developed by us and our friends. So what I have shown in this talk is the ZTF simulation, and it's in a paper that just published on arXiv today. So you're welcome to take a look. And there are examples for simulating Roman, highlighted you time domain survey, examples for simulating TP2, and there are also example for simulating galactic RLI array stuff and microlensing stuff. And you're very welcome to check out all the tutorials we have on the on our documentation page. So we would like to collaborate with you to make LightCurveLynx as useful as possible. So the way you can contribute include writing new sources, writing new effects, or wrapping some popular package that you would like to use. For example, what we have wrapped include SN Cosmo and Dust Extinction and others. You're welcome to contribute extend to new instrument and service and extend core libraries. So here I just listed informations about our documentation, source code, and we have a Slack channel on LSST Discovery Alliance. You are very welcome to join and ask questions and contribute as you like. I hope after this talk, we will see you in the Slack channel and see you posting questions about and using these, using the software to do your own science. With that, I'd say thank you for your attention, and I will be happy to take questions.
Thank you, Mi. We do have time for some questions, and as a reminder, feel free to ask questions by raising your hand here on Zoom, asking in the Zoom chat, or posting in the LINCC Tech Talks channel on the Discovery Alliance Slack. Colin.
Amy, great talk. Very enjoyable. I had a quick question about the mixing and matching of the different surveys. And I saw they used the SVO, this filter profile service, which I love. Is that what's being used to sort of help make the data compatible with each other? Like if you're mixing the Z band from ZTF and Ruben, for example, how do you deal with the differences in the responses and whatnot?
Okay, so for mixing the surveys, we would want each survey to define their own passband. So there need to be a corresponding passband corresponds to the survey. So we're not really mixing the passband. Unless you think that's the same one and you can just define it as duplicates, but we want those to be specified. And this is mainly useful for, say, you want to see some, I have an example that was developed by Natasha. We are trying to see a joint simulation between Roman and Ruben, so that you're seeing light curves from those surveys, so like they can cover spaces that one is not see from the other. So I think that would be the main usage.
Awesome. Yeah, that's great. Thanks.
Reynolds, go ahead.
Hi, Mai. Thank you very much for the great talk. I'd like to ask you, going beyond the physical model, in the parameter model pipeline, is there any method for of data assimilation by the model that allows interpolation and resampling to make like different classes of transients as the standards? Because, you know, I ask this because of the common problem of sparsity in the real data. In other words, it's possible to simulate sparse light curves as we generally find in them in real data? Because your results are very good concerning the sparsity of the data for the supernova.
Yeah, thanks for the question. So we do have interpolation within the model. But I think right now it's still like a simple spline interpolation. So it really still depends on how good your model is. But like uh, if you want to like do Gaussian process on these light curves and provide the Gaussian process model, we can take that as the physical model. So we really don't want to like do a lot of these interpolation for the users because like there are different levels of like expectations like how these interpolations would be done. So we would expect users do that themselves, but it should be easily to import it into as a model and simulate, use whatever interpolation you're using.
Okay, thank you. Thank you.
And then say like I have a favorite supernova 1A model, like how hard would it be for me to go and integrate it into LightCurveLynx, like run the full pipeline?
So I guess it depends on like how your model is structured and how your model input is. So we have like some standard ways that we can do that. For example, if it's a ICD model with columns of time and wavelengths and fluxes, we can simply just read in this table, and I believe we have predefined methods to define the model. But if it's like more complicated things that you include different parameters in different ways, there need to be some work to define all these parameters and include them. So yeah, I guess it really depends, but we have some documentation about these, and we are also very happy to collaborate to make this happen.
Thank you. Um, all right, so thanks again to me for a fantastic talk, and thanks to everyone for attending the Link Tech Talk series today. Our next Tech Talk is scheduled for May 14th, 2026. Stay tuned for an announcement. Oh, wait, hang on. We've got a chat. Oh, fantastic. Here's a link to the documentation for adding new models. And also, I guess the read the docs will have a lot of fantastic. Okay, thank you. And so our next Tech Talk will be next month, May 14th. Stay tuned for the announcement. We'll be hearing about Redback, which is integrated with LightCurveLynx from Nikhil Saran. In interim, please join LSST DA Link Tech Talk Slack channel and the link at list.lsst.org mailing list for more information and future announcements. There's more information, including links to the Rubin Community Forum and a calendar at our LSST Discovery Alliance website. LINCC Frameworks is also holding office hours every Thursday at 10 a.m. Pacific, 1 p.m. Eastern, except when it conflicts to this Tech Talk series. So if you want to check out like LightCurveLynx and try making some simulations yourself, you're totally welcome to show up next week and ask us questions in person to help you get jump started into this. Then if you have an idea for a Tech Talk, we'd love to hear from you. Feel free to reach out to us on the Slack or by email listed on the Tech Talk webpage. With the speaker's permission, today's Tech Talk will be available on our YouTube channel within the next few days. And you're always welcome to ask any questions on that channel too. Have a great rest of your day or night. Thank you so much.
Thank you.
Thank you. Bye-bye.